All right, let's dive into some physics. We're talking wave interference today.
Right.
And you even sent us a link to a simulation from Open Educational Resources, Open Source Physics at Singapore.
Oh, cool.
It's a ripple tank
No.
simulation, and it's built using something called
Using?
Easy JavaScript Simulations,
Okay.
or EJS.
Yeah.
But the website says it's a work in progress.
Interesting. What's interesting about this is that even though it's incomplete,
Yeah.
it can still give us some insights into wave behavior. The creators say it's missing certain 2D scalar elements,
Okay.
which are really important for representing the complexity of how waves interact.
Gotcha. So before we go too deep into that, can you give us a quick overview of what a ripple tank is and how it helps us understand waves? I'm picturing like a mini swimming pool for science experiments.
Well, that's not too far off.
Okay.
A ripple tank is basically a shallow tray.
Okay.
Filled with water,
Oh.
usually with a light source shining above it. And by creating disturbances in the water, you can generate waves and observe their behavior.
Oh, okay, cool.
The shallow depth basically makes the waves two-dimensional, which makes studying them much easier.
Oh, that makes sense. So it's like a controlled environment for studying waves in action.
Yep.
You mentioned earlier that the simulation is missing some scalar elements.
Right.
What exactly are those, and how does their absence how does it affect what we're seeing in the simulation?
Well, scalar elements in this context would be things like the height or intensity of the waves.
Mm-hmm.
Think of it as adding another dimension
Gotcha.
to the visualization.
Okay.
Without them, we're missing out on crucial information on how the wave amplitudes vary.
I see.
It's kind of like watching a movie without sound.
Okay.
You get the visuals,
Yeah.
but the full experience is lacking.
Right, right. Okay, so those missing elements would give us like a much richer and more accurate representation of the wave pattern. I'm already wondering how much more we could learn if they were included.
I know, right?
But let's focus on what we can learn, even with those limitations for now.
Sure.
You mentioned wave interference.
Right.
What does that mean exactly?
So imagine two waves
Okay.
traveling toward each other in the ripple tank.
Yeah.
When they meet, they don't just pass through each other. They actually interact. And that interaction is what we call interference.
Oh, okay.
And there are two main types, constructive and destructive.
Constructive and destructive. Those sound pretty interesting. Can you break those down for us?
Yeah, so in constructive interference, the crests of the two waves, they align perfectly.
Mm-hmm.
And when this happens, they add together and you get a wave with a larger amplitude, basically a bigger wave.
Oh, so it's like if you have two friends pushing a swing at the same time.
Right.
It's going to go higher.
Exactly. Their forces combine.
Right. Okay. So in constructive interference, the waves are basically amplifying each other. What about destructive interference? Is it the opposite?
Yuck it. In destructive interference, the crest of one wave meets the trough of another.
Right.
And instead of adding together, they cancel each other out.
Wow.
So you end up with a smaller wave or even no wave at all.
So it's like those same friends pushing the swing, but in opposite direction.
Exactly.
It's not going to go anywhere.
Their efforts are working against each other.
I hadn't thought of it like that. The swing analogy really helps. So we're seeing these interactions in a ripple tank.
Yeah.
But where else does wave interference happen in the real world? I feel like it's got to be more common than we realize.
You're absolutely right. It's all around us.
Okay.
Take noise-canceling headphones, for example.
Yeah, those are great.
They work by generating sound waves that destructively interfere with incoming noise.
So they're making it quieter for the listener.
Precisely.
Wow. So my headphones are like tiny physics labs on my ears, strategically silencing the world around me. That's incredible.
Right.
What other examples are there?
How about two musical instruments playing the same note?
Oh, yeah. Okay.
Depending on their position relative to you, the sound waves they produce can interfere constructively, making the note louder.
Okay.
Or destructively, making it softer.
Oh, wow.
You're literally hearing the physics of wave interference in action.
That makes me wonder if, like, sound engineers,
Yeah.
if they use this when they're mixing music.
Interesting question.
But what about light waves? Do they do interference too?
Absolutely. The iridescent colors you see in soap bubbles
Cool.
or oil slicks are a direct result of light interference.
Okay.
Light waves reflect off different layers of the thin film, and depending on the thickness and the angle, certain wavelengths interfere constructively, creating those vibrant colors you see.
It's like nature's light show, orchestrated by physics. It's amazing how something so simple, like a soap bubble, can show such intricate wave interactions.
Right. And it's all thanks to understanding basic concepts like wave interference. Once you start looking for them, you see them everywhere, and it changes how you see the world around you.
That's so true.
Yeah.
And even this ripple tank simulation, even though it's a work in progress, it helps us visualize these interactions.
Exactly. Visualization is super powerful, even with its limitations.
Yeah.
Models like the simulation help us see wave interactions unfold
Hmm.
and grasp the concepts more intuitively. Imagine if those missing scalar elements were there. We
Yeah.
could see the varying wave heights and maybe even spot more nuanced patterns.
It makes you realize how much work goes into creating these educational tools. And speaking of tools, you mentioned that this simulation is built using something called EJS,
Yeah,
fixed
easy.
JavaScript simulations.
Right.
What exactly is that? And what makes it so valuable for learning?
Well, EJS is a platform for creating interactive simulations
Okay.
for education.
Hmm.
What sets it apart is that it's interactive. You can change variables in real time
Oh, cool.
and immediately see how that affects the wave patterns.
Oh, wow.
It's like having a virtual ripple tank right in front of you.
Okay, yeah.
You can experiment and test your understanding.
So you're not just passively watching, you're actively engaging with it.
Exactly.
I bet that makes learning a lot more effective.
Definitely. The website that hosts the Ripple Tank simulation, Open Educational Resources, Open Source Physics at Singapore, actually has a bunch of other EJS examples
Nice.
covering all kinds of topics, from mechanics to electromagnetism.
Okay.
It's a treasure trove of interactive learning opportunities.
I'm adding that to my list of websites to check out. I love how it makes these complicated science concepts
Yeah.
more accessible and engaging.
It sparks curiosity and encourages exploration.
Now, before we move on to explore different interference patterns, I'm curious, do you know anything about where ripple tanks came from?
Oh, that's interesting.
Like, how did someone get the idea to study waves this way?
Well, the origins of ripple tanks can actually be traced back to observations of water waves in nature.
Oh, okay.
Someone, somewhere, had the bright idea to recreate and control those waves in a simple environment.
Makes sense.
And that led to developing this really valuable tool for studying wave phenomena.
It really makes you wonder how many everyday things have the potential for scientific discovery.
It's true. All it takes is that spark of curiosity and asking, how can I learn more about this?
Absolutely.
Yeah.
And that's what makes science so cool. It's just a constant journey of
Yeah.
observation and experimentation and discovery,
Right.
just wanting to understand the world around us.
Exactly.
Well said. Okay, let's recap what we've learned so far.
Okay.
We've learned what ripple tanks are
Okay.
and how they help us visualize wave interference
Right.
and the difference between constructive and destructive interference. We even talked about how wave interference shows up in sound waves
Right.
and light waves
Yeah.
and in everyday things like noise-canceling headphones.
Exactly.
But hold on. Our exploration of wave interference is just getting started. When we come back, we'll dive into some specific interference patterns
Okay.
and their applications in different fields. Stay tuned.
Awesome. Welcome back to our deep dive on wave interference. I'm excited to dig a little deeper into some specific types of interference patterns.
I'm ready for more.
Yeah.
We talked about constructive and destructive interference generally,
Right.
but I have a feeling there's like a whole world of patterns out there.
You're absolutely right. The patterns that emerge from wave interference can be incredibly intricate,
Okay.
even beautiful sometimes.
Oh, wow.
A classic example is the double slit experiment.
Oh, the double slit experiment.
Yeah.
I've heard of that one.
It shows how light acts like a wave, right?
Yeah, I think
In
so.
a ripple tank.
Okay.
We can simulate this by generating waves
Yeah.
from 2-point sources,
Right.
which act like the 2 slits in the experiment.
Gotcha.
And as the waves spread out from those sources, they interfere with each other
Okay.
and create a distinct pattern on the water surface.
Okay, I'm trying to picture it. What does this pattern look like?
Right.
And what can it tell us about waves?
Well, the pattern has alternating bright and dark bands, or in our ripple tank, areas of high and low wave amplitude. And these bands, we call them interference fringes.
Interference fringes, okay.
And they're a direct result of constructive and destructive interference.
So the bright bands, those are where the waves are constructively interfering,
Right.
creating bigger waves.
Exactly.
And the dark bands, those are where they're canceling each other out.
You got it. Through destructive interference.
Okay, that makes sense. And what's really cool is that the position and spacing of these fringes, it actually depends on the wavelength of the waves.
Yes.
And the distance between the two sources.
Precisely. So by looking at the interference pattern, we can figure out stuff about the waves themselves.
That's amazing.
Isn't it? And this works not just for water waves,
Okay.
but for light waves
Yeah.
and even sound waves too.
Wow.
The double slit experiment is super important in physics because it proves that light behaves like a wave.
That's pretty wild. So you're telling me that a simple experiment like that can reveal so much about the nature of light.
It really can.
Now, remember how you mentioned the ripple tank simulation is missing some 2D scalar elements?
Right.
Would those missing elements, would they help us understand the double slit experiment better if they were there?
That's a great question.
Yeah.
The current simulation does a good job of showing the basic principles.
Okay.
But having those scalar elements would definitely give us a more detailed view.
Okay.
For example, being able to see the changes in wave height
Mm-hmm.
would let us see the contrast between the bright and dark fringes even more clearly. It would be like adding another layer of depth to the whole thing.
So it would make the constructive and destructive interference even more obvious.
Exactly.
I see. I see. Okay, so we've explored the double slit experiment.
Mm-hmm.
Are there any other cool interference patterns we should know about?
Oh, definitely. There's another really interesting phenomenon called diffraction.
Diffraction, okay.
It happens when waves come across an obstacle or go through a narrow opening,
Okay.
and instead of continuing in a straight line,
Yeah.
the waves bend around the obstacle or spread out from the opening.
Oh, so it's like the waves are rebelling against boundaries.
Kind of. You've probably seen this happen with ocean waves near a pier or something.
Right, exactly.
And just like interference.
Okay.
Diffraction happens with all kinds of waves. Sound waves, light waves, you name it.
Okay.
In fact, the way sound waves diffract around corners is why you can hear someone talking in another room even if you can't see them.
Oh, that's true. Okay, so diffraction is basically waves taking the scenic route, bending and spreading out when they hit an obstacle.
That's a great way to put it.
But does it create any particular patterns, like we saw with interference?
It does. When waves diffract through a narrow opening, like a single slit,
Okay.
they create a pattern of alternating bright and dark bands, kind of like the double slit experiment.
Oh, interesting. So it's similar but also different. What makes a diffraction pattern unique?
Well, in a single slit diffraction pattern, the central bright band is much wider
Okay.
and more intense than the other bands.
Okay.
And the pattern is symmetrical,
Okay.
meaning it looks the same on both sides of that central band.
So by looking at the pattern, we can tell if the waves went through a single slit or a double slit.
That's right. The pattern gives us clues about the obstacles the waves encountered.
It's like a detective game, but for waves.
Exactly.
But these patterns, they're not just cool to look at. Do they have real-world applications?
Oh, absolutely.
No.
Diffraction gratings, which are surfaces with lots of closely spaced slits,
Okay.
are used in spectrometers to separate light into its different wavelengths.
Oh, interesting.
This lets scientists analyze what materials are made of.
Oh, wow. So that's how scientists know what stars are made of? Or like how they identify unknown substances by the light they emit?
Exactly. Diffraction is also key in X-ray crystallography.
X-ray crystallography.
It's a technique used to study the structure of crystals.
Wow, I've heard of that.
By shining X-rays onto a crystal and analyzing the diffraction pattern, scientists can figure out how the atoms are arranged within the crystal.
That's amazing. So diffraction helps us understand stuff at the atomic level. Are there any other examples?
Diffraction is also essential in telecommunications. Fiber optic cables,
Oh, yeah. Okay.
which carry tons of information as light pulses, rely on diffraction to guide the light along the fibers.
So without diffraction, those light signals wouldn't travel very far.
Right. They would dissipate really quickly, and long-distance communication would be impossible.
That's incredible. A phenomenon we can see in a simple ripple tank is so important in technology and research. It shows how everything in physics is connected.
It really does. It's a great example of how basic principles can explain all sorts of things.
So before we move on from wave interference,
Yeah.
I'd like to touch on the importance of visualization again. We talked about how the ripple tank simulation has some limitations,
Right.
but it's still been really helpful in understanding these concepts.
Visualization is key when trying to wrap your head around complex scientific ideas.
Yeah.
Even with limitations, models like this ripple tank, they allow us to see these abstract principles come to life. They bridge the gap between theory and reality,
Okay.
and that makes learning more engaging and intuitive.
It's like we're seeing this invisible world of waves we can actually watch those interactions happen.
Exactly.
It makes you appreciate the beauty and complexity
Yeah.
in even the simplest things.
It really does. The world of waves is vast and full of surprises.
All right, let's take a moment to let all this information sink in. When we come back, we'll wrap up our deep dive into wave interference and give you some final things to think about. Stay with us. We're back and ready for the final part of our deep dive into wave interference. It's amazing how much we've learned about waves.
I know, right?
It's like changed how I see the world.
It's pretty fascinating how these concepts, once you get them,
Yeah.
you start seeing them everywhere.
Oh, speaking of which, I'm remembering back to our discussion on EJS simulations.
Right.
The website with the Ripple tank, open educational resources, open source physics at Singapore.
Mm-hmm.
They also had some examples related to lenses and optics.
You're right. Yeah, they had a bunch of EJS simulations that focused on light.
Oh, okay.
Including models showing refraction through lenses, reflection from mirrors, and even the principles behind things like telescopes and microscopes.
Oh, cool. Well, now that we've talked about wave interference, I'm even more curious about how lenses work to create images.
Yeah.
I imagine there's a lot of interference and diffraction going on in those little pieces of glass.
Absolutely. Lenses work because of refraction.
Okay.
Which is when light bends as it passes from one medium to another, like from air into glass.
Right, right.
The shape of the lens is designed very precisely to control that bending.
Gotcha.
Making light waves converge or diverge to create those images.
So it's like the lens is like a choreographer directing the light waves to make the images we see. And I bet interference and diffraction are really important for how sharp and clear those images are, huh?
You're exactly right. The way light waves interfere with each other after going through the lens determines how sharp, clear, and even the colors in the image.
Okay.
Diffraction can limit how detailed an image can be,
right?
Especially with small objects or fine details.
It's crazy to think that something as simple as a lens depends on such complex wave interactions. It shows how interconnected physics really is.
It does. It's a great example of how things that seem totally different are actually tied together by fundamental principles.
I think we've reached the end of our wave of knowledge. Before we wrap up, I want our listeners to feel like they can keep exploring wave interference on their own. Do you have any final thoughts or advice?
I would say pay attention to the world around you.
Okay.
Look for examples of wave interference and diffraction in your everyday life. Listen to the sounds you hear. Look at the things you see. Think about the technology you use. You'll be surprised how often these principles are at work.
That's a great point. It's like a physics scavenger hunt. And who knows, maybe making those observations will spark new questions.
Exactly.
And lead to some amazing discoveries. That's often how it happens in science. Simple curiosity leading to profound insights.
Couldn't agree more. Remember, even the most basic observation can lead to something extraordinary. Never stop asking why.
So well said. On that note, we're going to bring our exploration of wave interference to an end. We hope you enjoyed riding this wave of knowledge with us. Keep exploring the amazing world of physics, and until next time, stay curious.